In this video, I will describe how to solve a system of three equations, each having three variables, with the substitution method. Now, there are other methods to solve a system of equations like this, but the substitution method for solving a system is an excellent tool to have in your algebra toolbox. This is a system of three equations with three variables, and the solution is a value for x, y, and z that makes all three equations true statements. There are actually an infinite number of values for x, y, and z that would make the top equation equal to negative 27, but there is only one x, y, and z that will make all three of these equations true. And we will find that those three values using the substitution method in 4 steps starting now. Step 1 out of the 4 steps in solving this system with the substitution method is to consider the first equation and solve that equation for x. Isolate the value of x in the first equation. What we'll do is we'll focus on this first equation, ignore the other two temporarily, and solve for x. And this is very basic algebra. We can solve for x, isolate x by adding 3y to both sides of the equation and adding 4z to both sides of the equation. So those will be joined with negative 27 on the right side of the equation. And then we have to take care of the negative sign in front of x, and that can be accomplished by multiplying all terms on the right and left side of the equation by negative 1. And that results in x being isolated. We now know that x is equal to negative 3y minus 4z plus 27, and we will use that in the next step. Now that we've solved for x in the first equation, step 2 will focus on the second equation. Using the second equation, we will substitute into that second equation our expression we found x to be, and then solve that second equation for y. So in this step, we will ignore the first and the third equation. We'll focus on the second equation, substitute our expression for x, and then solve for y. First, substituting this expression for x into this second equation, we'll replace x with what we found x to be in step 1, negative 3y minus 4z plus 27. And now we'll have to do some algebra to isolate y. We want to take this equation, which now actually only has two variables, y and z, and isolate y. Solve this equation for y. We'll start by distributing negative 3 through the quantity of negative 3y minus 4y plus 27. Negative 3 times negative 3y is 9y. Negative 3y times negative 4z is positive 12z. And the product of negative 3 and 27 is negative 81. There'll be a lot of multiplications involving positive and negative numbers as we work through this process. Be careful. Missing one will cause your final answer to be incorrect. At this point, I have like terms on the left side of this equation. There are two terms involving y and two terms involving z. 9y minus 1y is 8y. 12z and 6z add up to 18z. I will subtract 18z from both sides of the equation and add 81 to both sides of the equation, furthering along the process of solving for y. There's one step left in solving for y, and that will be to divide all terms on both sides of the equation by 8. We'll start to have some fractions involved in this problem, and when solving systems of equations with the substitution method, you will often run into fractions as coefficients. Careful, put them in lowest terms if you can, and the process isn't too difficult if you're careful. Dividing all terms by 8 results in 18 over 8z negative, which in lowest terms is negative 9/4 z, and 108 over 8 is 27 halves. We've solved the first equation for x. We've solved the second equation for y. And now we're at step 3, which we will use the third equation during. This third step is probably the most involved. There's a lot of algebra in this step. What we'll do with this third equation is first substitute the value for x into the third equation, then substitute the value for y, into the third equation, and at that point, we'll be able to solve for z. And when I say solve for z, I mean we'll actually find a value for z. It will not be an expression involving other variables like we found with x and y. We'll actually find part of our final answer here in step 3 after doing, like I said, somewhat of a lot of algebra. So again, we're going to take this third equation. Ignore the other two for now. Take the third equation, 6x plus 2y minus 4z equals -6. We're going to end this step by solving for z. But to do that, we sort of have to get rid of the x and the y. And the way that we'll do that is the substitutions, the namesake of this process. First, substituting for x, we'll replace 6x with -3y minus 4z plus 27. Then we'll substitute for y. But there are actually two occurrences of y at this point in the equation. Two occurrences of y. There's one in the quantity that was representative of x, and then there is one from the original third equation as a coefficient of 2. We have to substitute this expression for y twice. That results in sort of a complex algebraic expression. There's a lot going on here. We have fractions involved, some positives and negatives, but it's nothing too difficult if we take our time and carefully now move on to the third step in step 3, the third part of step 3, solving for z. To solve for z, I'm going to have to use the order of operations, work from the innermost grouping symbol out, and this is going to involve first distributing a -3. Distributing a -3 results in -3 times -9/4 z is positive 27/4 z minus -3 times 27/2 is -81/2. Then there's a -4z, a plus 27, and I haven't done anything with the rest of this equation at this point. All that has happened on the screen so far is the distribution of -3. Now at this point, I'm going to go ahead and distribute the 6 through the 4 terms that are inside of this quantity, and I'll distribute the 2 through the 2 terms in the next quantity. The -4z and the -6 will be tagged on at the end. Distributing the 6 through all 4 terms results in 81/2 z in lowest terms, minus 243. 6 times 81/2 is exactly 243 with the minus sign. 6 times -4z is -24z. We have a product. The next product is 162. Then distributing the 2 to -9/4 z plus 27/2 results in -9/2 z plus 27. And then, like I said, the -4z and the -6 come along at the end. At this point, most of the hard work is done. All that we'll do now is combine the like terms and isolate the z. There are actually 4 terms involving z, which I've highlighted in red here, and 3 constants on the left side of this equation. I'll combine those. 81/2 minus 24 minus 9/2 minus 4. All of those together have a sum of 8z. And the constants, -243, positive 162, and positive 27, have a sum of -54. And that's all equal to -6. Very manageable equation at this point. Let's add 54 to both sides of the equation and divide by 8, and we have a value for z. We actually have part of our final answer at this point. Z equals 6 will be the z coordinate in the final answer to this system. We've now found that z is equal to 6, and we can move on to step 4, which I think is the easiest step. And in this step, we're going to use the results from step 2 and then step 1, and we're going to do some substitutions of z equals 6. First, we'll use the result from step 2. We'll substitute z into that result from step 2, and that will give us a value for y. So at that point, we'll know that z is equal to 6 and y is equal to some other number. And once we know those two things, we'll substitute those two values into the result from step 1 and easily find x and have the solution to the system. So first, we're going to use the result from step 2. At the end of step 2, that was where we solved the second equation for y. We found that y was equal to negative 9/4 z plus 27 halves. So we're just going to substitute our value for z, 6, into this expression and easily get a y. Negative 9/4 times 6 plus 27 halves is a basic arithmetic problem. That will tell us that y is equal to negative 27 halves is the product of negative 9/4 and 6 plus 27 halves is, I don't think that we need a calculator for this, 0 halves or 0. So we now know that y is equal to 0. We have 2/3 of our solution. We know z is 6 and y is 0. Now what value for x, in addition to y being 0 and z being 6, makes all three of these equations in the system true statements? We can find that using the result from step 1, which was, that was when we solved the first equation for x and found x to be negative 3y minus 4z plus 27. We'll now substitute y equals 0 and z equals 6, and very easily we'll be able to identify the value for x. Substitute 0 for y, 6 for z. Negative 3 times 0 is 0. Negative 4 times 6 is negative 24. And we can see here that negative 24 plus 27 is 3. That's the value for x in the solution to this system of 3 equations. So we now know x equals 3, y equals 0, and z equals 6 is the solution to this system of equations. This is the final answer. This answer can be verified by substituting a 3 for x, a 0 for y, and a 6 for z in all 3 equations. If you substitute these 3 values in for x, y, and z in the top equation, the left side of the equation will equal negative 27. In the second equation, it will be positive 27, and the third equation will be negative 6. These are actually the only 3 values for x, y, and z that would make all 3 of these equations true. And that's why x equals 3, y equals 0, z equals 6 is the solution to this system of equations.